I'm Charles, and I'm on a mission to find what's inside everything. To help me get my answers, I have an industrial CT scanner. It takes a whole bunch of X-ray images from all around a subject, and then builds a 3D model revealing every internal detail. Today, I've got an integrated camera gimbal to take a look inside of. Because it's camera gear, I can actually screw it directly onto the base plate of the machine and let it scan. A gimbal keeps the camera straight and level, even though the handle may be shaking or rolling around. These have become far more common in recent years as the prices have fallen dramatically. You can get something like this that holds your phone for about $100. What is it about these joints that keeps them so smooth and lets them spin with so little resistance? Let's look inside. Let's talk about how these gimbals work. We have a plastic housing around all of the electronics and all the mechanical parts. Starting at the bottom, battery cell, and working on up, we've got a big bundle of electronics here. And then we get to the part where we have to start actually asking some questions that I can answer. Namely, how the heck is this thing so smooth and precise? What is it about the way they've designed these joints, these actuators, that makes it so slick in operation? On this, both ends of this final ball are supported. Somewhere in here, we're gonna need to have a bearing and a motor. And sure enough, we find a motor and a bearing. Clearly we need to get a bunch of signals between that terminal ball and the electronics back in the handle. How are we handling that here? Well, looking at this, we can see a bunch of wires going up and through this top bearing and emerging out here where they're in the next part of the joint stack up. All of those are just routed straight down the middle of this bearing. Oops. Yeah, they're just straight down the center raceway of that bearing. There are your balls, there's your inner race. Wires come up and pop right on out. That makes a lot of sense because you only have a limited range of motion on this joint, and a slip ring that can handle these very high frequency signals coming from the 4K camera on board would be huge, expensive, and probably kind of sticky. We don't want sticky, we want smooth. So down at the bottom end, we encounter this motor. Now this motor is what's doing the active control. So we're gonna need to have some sort of, well, precision control on it. This is very likely to be a 3-phase brushless motor. So we should expect to find some electrical connections on it somewhere. Oh, okay. So cutting it down to just the motor, we can actually see our 3 electrical signals here, here, and here. Those are phases U, V, W, or ABC of this motor. So those should have wires coming off them, going up to wherever the control electronics are. And there we go. Okay, so these are soldered onto what looks like a circuit board, almost. But then, if it was a circuit board, the connections would have to be in plane with it as well. And they're not. Instead, it's a flat, flexible ribbon cable. It works its way up. These three connections turn into 6 wires, which are now over here, and they sweep back up, and they go into a board mount connector right here. So that's what's bringing the power from the motor controller, which we'll track down in a minute, down into the motor itself. Curiously, it's only the 3 power signals, so we haven't actually found how we're getting any position feedback yet. But it's got to be in there somewhere, and it's got to be somewhere where the stationary part and the rotating part are relatively close to one another. Bingo! This is a Hall effect rotary encoder. So that's an integrated circuit that can detect the orientation of a magnetic field that it's in. There's your magnet right underneath it, has a magnetic field to it that passes parallel to the face and across the diameter. What that means is that as it spins, this chip can figure out the exact orientation of the rotor of that motor and feed that into the motor controller. With an encoder like this, which can get you, I don't know, probably 12 to 14 bits of resolving power, you're able to control the orientation of that motor. You can get 2 to the 14 steps of resolution, so 1/16,000th of a turn of control out of that motor. Beautiful way of doing this, and this is what a lot of modern servo drives do. So we have just this little circuit board here. Oh, that's cool. Okay, so the electrical contacts for this rotary encoder, you see them, they're racing away this way,
And as we sweep up through the stack, they just kind of become this wire, this flat cable here. And that's because this rectangle isn't a circuit board necessarily. It's actually a stiffened piece of a flat, flexible circuit board. That's pretty cool. Let's see if we can find that in the 3D view itself. Oh boy. There's our rotary encoder. There's our magnet. Let's see if we can find the actual thing it's mounted to. Crank this wide open. I think we can almost make it out here. Down here are our motor wires in this ribbon. And right here is the edge of that flat flex ribbon. Yeah, so that is actually the material the circuit board is made of. It snakes down and it becomes the second circuit board on a different plane that we actually have our rotary encoder mounted to. I think the entire motor control section of this, with the feedback encoder, is a single piece that gets assembled on a line and then bent into place with all of those components on it already. That's really cool. I think we've kind of found all the secrets. What's going on this board here? So we have 3 chips, A, B, and C. We have this 4-pin connector. We had our 6-pin connector going to the motor right here. Everything else is just support components, capacitors, resistors, things you need, but don't really need to talk about. So one of these is going to be a microcontroller. Microcontroller does some computation and sends signals to another chip. And that other chip is going to be the motor controller, which that is going to be taking the power in and outputting it into the 3 phases. That's our inverter. It appears to be fully integrated into a single integrated circuit. Third one of these is going to be an inertial measurement unit. What that's doing is it's telling the computer somewhere else in this system how the head of this thing is oriented. And with that, you can actually create all the signals required to tell each joint how to balance out and keep the head level and smooth. But how is all that communication happening? Well, this 4-pin connector right here is actually everything that's needed for the whole communication system to take place. What this is going to be is it's going to be 2 pins that are power and 2 pins that are a shared communication bus. Those 4 wires are going to be shared through all of the different joints in this system. One more fun detail before we move along. Right here, in behind the image sensor, there's this big disc. And I had to chew on this one for a moment before I figured out what it is, because it's stupid. That's just a piece of steel that they put there to counterweight this whole thing, so that if you're holding this sideways, for instance, this floats more or less level, and you don't have to be fighting gravity in order to maintain stability on this axis. That's pretty cool. They achieved that with just one piece of steel put in the right spot, which is really silly, but also I respect it.
If you enjoyed this video, make sure to leave us a like. And if you want to see inside of something, leave a comment with your suggestion. If you want to support the channel, share this video with a friend, or check out hacksmith.store. And if you want to see inside of everything, get subscribed.